After talking about average rates of change, it's important now to focus on what it means to be an instantaneous rate of change. The average rate of change of a function, as we have learned, over a specified interval, a to b, let's say, is defined as what? Well, that's basically just the slope between those two endpoints of that secant. So the slope is going to be, if we look, if our function is f, then the y value of that point will be f of b, and the y value of this point will be f of a. So to find the slope between 2 points, we simply do the difference of the y's over the difference of the x's, or the rise over the run. So that would be f of b minus f of a over b minus a. And so that's your average rate of change. It's a slope calculation. On the other hand, if we want to talk about an instantaneous rate of change, that's going to be the slope of a tangent line to our function at a single point. So if we want to find the instantaneous rate of change of a function f at x equals a, we need to find the slope of the tangent line to that curve at x equals a. So this green one is our function f, or f of x. You can write f of x if you like. And the purple line is your tangent line. So how do we find the slope of this tangent line, which represents the instantaneous rate of change of our function f at a? How do we find the slope of that tangent line if we only have a single point? We need 2 points to get the slope of a tangent line, or of any line. So what we're going to do is we're going to create another point. And we're going to create a point that's pretty close to our first point. Let's say it's h units away. We're just going to let h be a really small number. Like, for example, if a was 4, maybe h is 0.1. So it'll be 4 and then 4.1 on our x-axis. And so now with that, we can calculate the slope between those 2 points on our function, and that should be close, not exactly equal to, but that'll be close to the slope of the tangent line to our function at a. It won't be exact, but it'll be close. And if I pick this h to be even smaller, then that second point will get closer and closer to the first point, and the slope of the secant between them is going to get closer and closer to the slope of my tangent line. And so then maybe if h is even smaller, then those 2 points get closer and closer together. And then the slope between those 2 points becomes closer and closer to the slope of my tangent line. And so after talking about limits, you understand that I could take the limit as that second point gets closer and closer to the first point of the slope between those 2 points, and that limit will actually equal the slope of my tangent line. So, what is the slope between those 2 points? Well, that's going to be f of a plus h minus f of a over a plus h minus a. And as you can see, the a's will cancel in the denominator. And so if I take the limit as h approaches 0 of that slope calculation, that is actually going to equal the slope of the tangent line. And so that's the basic idea behind the instantaneous rate of change. So as h gets smaller and smaller, closer to 0, the slope of that secant will get closer and closer to the slope of the tangent line. And so there we have it. And we have a special name or special word for the slope of a tangent line, and that's called a derivative. A derivative is the slope of the tangent line, or sometimes in IB they call it, instead of slope, they use the term gradient. So the slope or gradient of a tangent line is the derivative of the function, which is the instantaneous rate of change. So all these terms mean the same thing. Instantaneous rate of change. At a particular point. So slope of the tangent line, instantaneous rate of change, derivative. All mean the same thing. So let's go ahead and try that for a specific example. Let's find the gradient or the slope of the tangent line to this function, a nice parabola, at x equals 3. So remember, the idea here, we have y equal x squared, looks something like this, and then at x equals 3, we want to find the slope of the tangent line. So we're going to pick a second point that's close to here and calculate that slope, and that point will be 3 plus h, and then the limit as h approaches 0 of that slope will equal the slope of the tangent line. So we need to calculate the limit as h approaches 0 of f of a plus h minus f of a all over h. That's our general calculation for the slope of the tangent line. Now for this particular example, we know what the function is. The function is y equal x squared. And we know what a is. A is equal to 3. So, let's erase this and draw some arrows. So my function, f of x, we know what that is. And my value for a, we know what that is. So now we're just going to go ahead and evaluate this. So to find the slope of the tangent line, we're doing the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. So the limit as h approaches 0. What is f of 3 plus h? Well, I'm going to plug in 3 plus h for x. So it's going to be 3 plus h squared. That's f of 3 plus h. What's f of 3? Well, that's 3 squared all over h. And so now we're just going to do some simplification and maybe algebraic manipulation to see if we can figure out what this limit is. Obviously, we can't just plug in 0 for h right now, because we'll get it divided by 0. So let's square 3 plus h. That'll be 9 plus 6h plus h squared, and then minus 3 squared, which is 9, over h. The 9's cancel on top. And now I can factor in h out of both terms on top. And so I'm going to have the limit as h approaches 0 of h times 6 plus h to the first over h. And those h's cancel. H divided by h is 1. And now I can evaluate this limit because I can plug in 0 for h, and I get 6 plus 0, which is equal to 6. And so that's the slope of the tangent line to that parabola at x equals 3. All right, so as I mentioned, the derivative of a function f at a point where x equal a is the gradient or slope, I should write that in there, of the tangent line to f at x equal a. And it represents the instantaneous rate of change. So notice, derivative, slope of the tangent line, instantaneous rate of change. All mean the same thing. They're all referring to the same thing. So any kind of a question, we could interchange any of those terms, and we're talking about the same exact idea. And we calculate it by doing the limit of that difference quotient. And the way we read that is f prime of a, and that represents the derivative of f at x equal a. So this is the notation for a derivative. It's the function with a little tick mark, and then in parentheses, a, which could be any number. F prime of 3, f prime of 7, f prime of negative 2. Let's try another one. Let f of x equal 1 over x. Find f prime of 2. Okay, so remember we're calculating the limit as h approaches 0 of the difference quotient, f of a plus h minus f of a, all over h. We know what our function is. That's defined there. We know what a is. A is 2 in this case. So we're going to do the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Now I'm going to plug in 2 plus h into this particular function. So that'll be 1 over 2 plus h. And then f of 2 is 1 over 2. And remember, that's all over h. So the rest of it is just going to be some algebra. And this is where some people usually get stuck or hung up on. So we have a complex fraction. What do we need to do? Well, we need to combine these two fractions. How do you subtract or subtract fractions? You have to have a common denominator. So what's the common denominator? Well, I'm going to need to multiply the first fraction by 2 over 2, and the second fraction by 2 plus h over 2 plus h. Then I'll be able to subtract the 2 and combine my fractions. So I have the limit as h approaches 0 of 2 over 2 times 2 plus h minus 2 plus h over 2 times 2 plus h all over h. I'm writing maybe more steps than you would need, but I want to make sure you understand all the techniques that I'm doing. Now I can combine those two fractions. So I have 2 minus, and be careful here, we're subtracting that entire second numerator. So put that in parentheses. And now this is all over h. So when you have a fraction within a fraction, that's the same. Dividing by h is the same as multiplying by the reciprocal, 1 over h. Let's simplify what we have on top. We're going to have 2 minus h. So we're going to have, switch colors on there. We're going to have the limit as h approaches 0. The 2's cancel, and I'll just have a negative h on top. And on the bottom, I'll have a 2 times a 2 plus h times an h. Now I can't plug in 0 to evaluate the limit, because I've got to divide by 0. But I can cancel negative h over h, simplifies to negative 1. And now I can plug in 0. And so I'm going to get negative 1 over 2 times 2 plus 0, which is negative 1/4. And so that is the slope of the tangent line to the y equal 1 over x graph at 2. And just to get a visual for that, what does 1 over x look like? That, and then we have another piece over here. And at x equals 2, that's somewhere over here. If I draw a tangent line at that point, it certainly is going to be negative. And I didn't draw the slope enough, but it seems like negative 1/4 is definitely a possibility. And you can verify it with a graphing calculator to look at that. Another example we can work through, g of x equals x minus 1. First, let's find the average rate of change over the interval 2 to 3. Remember, the average rate of change is just the slope of the secant. So it's just going to be f of 3 minus f of 2 over 3 minus 2. And so for this function, I used f, I should have written g instead of f. For this function, g of 3 is going to be 9 minus 1 is 8. G of 2 is going to be 3, and then 3 minus 2 is 1. So we get 5 over 1, or just 5. So that's the average rate of change over that interval 2 to 3. Now find the instantaneous rate of change at 2. So thinking visually, this is a parabola. At 2, if I calculate the secant between 2 and 3, that's going to be a little steeper than the slope of my tangent line at 2. So my answer should be smaller than 5. All right, so let's go ahead and calculate limit as h approaches 0 of, I keep wanting to write f, this is called g, g of 2 plus h minus g of 2 all over h. And I'm going to write it this way. So that's going to be the limit as h approaches 0. G of 2 plus h is going to be 2 plus h squared minus 1. And then minus g of 2, 4 minus 1 is going to be 3, all over h. So now I have limit as h approaches 0. If you simplify everything on the top, you're going to find that you're going to wind up with 4h plus h squared. Everything else will cancel over h. And then if you factor in h out of the top and cancel with the h in the bottom, you'll be left with the limit as h approaches 0 of 4 plus h. And now I can plug in 0 for h to get my limit, which is 4. And so that's the instantaneous rate of change at 2. Okay, so now you should be ready. We don't need to work through another example here. And the assignment is worksheet 1.